the talk is titled Spectral Geometry, Homogenization, and Minimal Surfaces. The goal by the end of this talk is to clarify what all of these things are, how they're related together, and what can we say about each of them from the other one. So this is based on joint work with Alexandre Giroir from Université Laval, Antoine Henrault from the Institut Élie Cartan de Lorraine, and Michel Karpoukin from Caltech. All right, so today, when I speak about spectral geometry, it will be around eigenvalue optimization. Geometric analysis, the main object will be free boundary minimal surfaces, and maximization of these quantities will give us free boundary minimal surfaces, and homogenization theory is a tool that we use, and we developed geometric homogenization in order to answer the questions that we asked, and we will see how all of these three things are related. So let me first talk about the setting here. I will stay in dimension 2, even though a lot of the results could be stated in higher dimension. We start with a closed surface M. It has a Riemannian metric. And when I write omega, I mean just some domain inside M. And of interest today will be the following two problems. First of all, the Laplace eigenvalue problem, where I look at Laplacian of u plus lambda u is equal to 0 in M. And here I don't need boundary condition because M is a closed surface. And the Steklov eigenvalue problem, where I look at harmonic functions inside the domain omega. And here, the particularity is that the eigenvalue problem is on the boundary of the domain, it's not inside. So I look at functions whose normal derivative are proportional to the function on the boundary of omega. Now, in both cases, the spectrum is discrete. It accumulates only at infinity. So the first eigenvalue is 0 in both cases and is associated to constant eigenfunctions. And then all the other eigenvalues are positive. There's a sequence of them. They go at infinity. And in both cases, these are the eigenvalue of an elliptic operator. In the first case, the Laplacian, obviously. In the second case, the so-called Dirichlet-Neumann map, which takes Dirichlet data on the boundary and maps out Neumann data associated to the harmonic extension. I will ask the following two types of questions. The first one is, given M, which metric G will maximize the first Laplace eigenvalue lambda 1 on the surface? And given M, which pair omega G maximizes the first Steklov eigenvalue amongst all domains and all metrics in M? And I also want to understand how are those two questions related. Are there actual maximizers? Are they only realized as limits? And because these two quantities here are not scale invariant, so if I want to maximize something that is not scale invariant, it doesn't really make any sense. We will maximize the following two functionals: capital lambda 1, which will be the first Laplace eigenvalue multiplied by area, and capital sigma 1, which will be the first Steklov eigenvalue multiplied by length. Both of these quantities are scale invariant or unitless if you would prefer more physical language. And these make sense to maximize amongst metrics, amongst domains. A first example of a quite important theorem in this business is Hersch's theorem from the 70s, which tells us that this capital lambda 1 on the sphere is maximized by the round metric, where we will have capital lambda 1 is equal to 8 pi. And so here we see that the optimal object has a lot of symmetries. This will come back, has as many symmetries as possible as for a metric on the sphere, I guess. And this is something that will come back in the future, also this value of 8 pi here. And the proof here is based on conformal invariance of the Dirichlet energy and the structure of conformal diffeomorphisms of the sphere. No, that's here. And the main goal of this talk will be how large can capital sigma 1 be for omega in the sphere. We will also answer it in a way for other surfaces as well, but the sphere will be our main objective here. Before I go on and talk about how we solve that question, let me talk about the link with minimal surfaces. So minimal surfaces, I don't know how many of you are well versed in geometry, but they're a classical object in geometric analysis which minimizes area locally. So in the classical approach, we fix a boundary, and Plato's problem consists in minimizing this area with a boundary fix. And the most well-known example of this is how a soap film between two wireframes will take this catenoid shape, not a cylindrical shape between the two circles. Now, one should think of minimal surfaces as a two-dimensional analog of geodesics. So geodesics will minimize length locally, whereas minimal surfaces do so for area. And we have this important characterization of minimal surfaces in Rn, which says that they are minimal if and only if the coordinate functions xk restricted to the minimal surface are harmonic. And so already we see the link with the Laplacian that we were talking about in the first part of the talk. An alternative approach to minimal surfaces is, instead of fixing the boundary at the beginning, we let the boundary vary freely on a hypersurface. So we can think of these free boundary minimal surfaces as the Neumann problem equivalent to the Dirichlet problem that would be Plato's problem where the boundary is fixed. And when you let the boundary vary freely, the boundary of the free minimal surface will meet the hypersurface on which this varies at a right angle. For the rest of the talk today, the hypersurface where the boundary varies will be a sphere of radius 1. This sphere could be in any dimension, not necessarily 3. And here are numerical examples of free boundary minimal surfaces in the unit ball, where we can see that this meets at a right angle. We have different topologies. And in fact, it's not that far ago that we started to have examples of free boundary minimal surfaces that had these non-trivial topology. In fact, until the work of Fraser and Shane, in 2016, we only knew the equatorial disk and the critical catenoid as free boundary minimal surfaces in the unit ball. There are, in the last 5 years, there's been many new ways of constructing them, some related to spectral theory, some unrelated to spectral theory. I will obviously talk today about those related to spectral geometry. So the first relationship between these free boundary minimal surfaces and the Steklov problem came into the work of Fraser and Shane in 2011, so a few years prior, where they proved that if omega is a free boundary minimal surface. Yes?
There is a question, so maybe before you continue.
Yes.
So Emil, you have a question?
You are muted.
This constraint at meeting at 90 degrees can be relaxed, for example, to any other number.
In fact, this is not a constraint here, in the sense that it's a theorem in a way that if you minimize area locally and you don't meet the boundary at a right angle, you could change the surface a bit to have a lower area. This is similar to when you try to solve the Neumann problem. You don't minimize amongst H1 functions which have normal derivative 0. You just minimize amongst H1 functions, or W12 depending on your language, and you find out that the solutions will have normal derivative 0 on the boundary. Are there any other questions before I go on? All right. Thank you very much for this question. So there is a theorem by Fraser and Shane in 2011 that says that if omega is a free boundary minimal surface in the unit ball, then its coordinate functions are Steklov eigenfunctions with eigenvalue sigma equals 1. Now, this is not a, it was a good insight to see. But once you think about it, it's actually not that surprising, because we already said that minimal surfaces have harmonic coordinate functions, and this is a condition for being a Steklov eigenfunction. And on the unit ball, because the normal derivative is just derivative in the radial direction, meeting the boundary at a right angle means that the normal derivative is equal to the function itself on the boundary. So in this case, the normalized eigenvalue, so if we remember, this capital sigma just meant that we multiplied the eigenvalue by the length of the boundary. So here, if I maximize the eigenvalue, it's maximizing the length of the boundary of this free boundary minimal surface. And there is a conjecture by Fraser and Lee that says that if a compact free boundary minimal surface is embedded in the unit ball, then the coordinate functions are Steklov eigenfunctions with eigenvalue sigma 1 equals 1. So the difference is here. In the first case, I don't know where in the spectrum is that eigenvalue. Okay? Sigma could be the first, it could be the 1000th eigenvalue. In this conjecture, it says that if you are embedded, this Steklov eigenvalue is actually the first non-zero one. And along with Alexandre Giroir, we have proved in the last year that the Fraser-Lee conjecture does hold if you have some symmetry, so the symmetries of a Platonic solid, and a prescribed number of boundary components. So in this case, indeed, the coordinate functions are Steklov eigenfunctions with eigenvalue sigma 1 equals 1. And here, you see other examples, and also the same as the ones I've shown at the beginning, of free boundary minimal surfaces satisfying those conditions. Now, we can observe a few things from there. We can see that as I have a higher and higher number of boundary components, well, I mean, you don't see that from the pictures, but the boundary length increases, and we can compute that. We see that the boundary components seem to distribute somewhat uniformly on these boundary. And this is maybe harder to see with the naked eye, but if you look on the right, the minimal surface itself seems to want to push itself against the boundary surface, whereas when I have a smaller number of boundary components, I go further down inside the sphere. So all of these observations are things that will be we will discuss in more details as we go along. So now in that same in their 2016 paper, Fraser and Shane have proved that you can not only go from free boundary minimal surfaces to Steklov eigenfunctions, but the other way around as well. So if I start with a surface with boundary, and I find an extremal metric, so it doesn't need to be a global maximum, for example, it could be local minimum or local maximum or anything of the sort, for this first normalized Steklov eigenvalue, then the Steklov eigenfunctions will be coordinates for an isometric immersion of omega as a free boundary minimal surface in a unit ball of some dimension. And so maximization of the first normalized Steklov eigenvalue will lead to free boundary minimal surfaces in the unit ball. And as with any time we do optimization within an infinite dimensional vector space, the question of existence of the extremal object is always a quite finicky question. Well, here maximal metrics always exist. That's been proved quite recently by Mathisen and Bitley. Now, we can ask how those maximizers that we find with this method, how do they behave? And they claimed in that same 2016 paper, they claimed that the following result holds. If I start with a surface of genus 0 with B boundary components, then necessarily with any metric, this first normalized Steklov eigenvalue is smaller than 4 pi. And as B goes to infinity, the embedding given by the maximal metric converges to a double equatorial disk, so it will collapse to 2 disks coming on top of each other. Now, of course, this is not the behavior that we see from any of these examples here. And in fact, in the same paper where we gave those examples, we proved that there is a sequence of domains in the round sphere such that this first normalized eigenvalue goes, in fact, to 8 pi. Now, 8 pi, the same value as the one we find in Hersch's theorem for the maximal Laplace eigenvalue, which is decidedly larger than 4 pi. We know that this 8 pi value has to be sharp. That's a result by Kokarev in 2013 using completely different methods. And our proof suggests that the correct limit of the embeddings is the boundary sphere, so that this behavior where the surface seems to push out against the sphere seems to be the correct behavior. But this is something that we're still working on. We don't have a proof of this fact. Now, if we look at the examples we had here, we already were above 4 pi, but still quite far away from 8 pi. And in order to push all the way to 8 pi, we need to talk about homogenization. Now, homogenization theory is a branch of applied mathematics. Some might even say industrial mathematics, where one studies composite materials that have a different microstructure at a small scale epsilon. Now, the problem is that very often PDEs that have a different macroscopic and microscopic behavior are, somewhat hard to study, whether we say hard analytically or numerically. And the reason for that is that often the tools that allow one to study the microscopic behavior are at odds with the tools allowing one to study macroscopic behavior. And since we cannot ignore any of the behaviors, we have to treat both of them at the same time. And the solution usually is to find, as the parameter epsilon goes to 0, an effective model towards which the PDE converges, and use that effective model in order to study the original PDE with a small epsilon. So these ideas are often used in shape optimization problems because it allows us to relax the optimization constraints, and often by having a larger space, we are able to find optimizers when they don't exist with more constraints. So here is an example of homogenization by obstacles. So if I start with my original domain, which is the boundary ellipse here, I could put many small holes, each at a distance epsilon from each other. Those holes, say here, would have a radius of about epsilon square. And as epsilon goes to 0, I will cover more and more of this ellipse. And I will, the holes will be smaller and smaller, be closer and closer together. And I can set up a PDE in this perforated domain. And here we use the fact that even though the domain is very irregular, around every one of those holes, I have a so-called reference cell. The geometry is very similar anywhere where I look inside. So I can set up auxiliary PDEs in these squares with a disk removed, for instance, if I want to study the limit properly. And for instance, I could look at this family of Steklov problems, harmonic functions inside, and the Steklov boundary condition both on the outside ellipse and on every one of the inside disks. And here I will have a so-called critical regime where the radius of the disks will be about beta over 2 pi epsilon squared. And this choice leads to the fact that the perimeter of the holes converges as epsilon goes to 0 to beta. Beta is just a real number times the area of omega. All right, well, if I do that, this is a theorem of myself with Alexandre Giroir and Antoine Henrault, then in this critical regime, all the perimeter normalized Steklov eigenvalues of the problem on omega epsilon converge to the area normalized Neumann eigenvalues. So this is just like the problem we had before, but again, with normal derivative of the function is 0. There's no epsilon here on the original domain. So in this case, this is our effective model for the Steklov problems on a problem on a domain with a small hole. And this is in this double limit here. Now, what does this allow us to say? This allows us to say that large area normalized Neumann eigenvalues imply large perimeter normalized Steklov eigenvalues. Because if I start with a domain here that has a large area normalized Neumann eigenvalue, then I can approximate that with a sequence of domains inside and reach as large a number with the Steklov problems. So there exists a domain in R2 such that its first normalized Steklov eigenvalue is about 3.39 pi. At that point, this was about 150% larger than any other examples known. And the reason why we have this is that we know that the disk maximizes the first Neumann eigenvalue, and that's about 3.39 pi. Yet we're still very far from 8 pi, still quite far below 4 pi. So we had to find a new method. And it was to, the new idea here was to do this homogenization limit on a surface, on a curved surface, rather than in a domain in Euclidean space, where we have the problem that we don't have the translation structure in order to very easily construct our domains. So here is how we construct the domains instead. We start with what is called a maximal epsilon separated set. This is just a set where every point is at a distance more than epsilon from each other. And if I add any point to my epsilon separated set, I lose that property. And I will partition M with what is called a Voronoi tessellation associated to that S epsilon. So what is that? Is that to every point of M, I associate the closest point of this S epsilon set. So everything in blue belongs to the black point at the middle. And here, these will be my reference cells. However, you can see that they are not all exactly the same shape. They're not exactly squares, all of them. And around every point in this set S epsilon, I will remove a disk with radius chosen so that the perimeter of the disk is equal to the area of the cell. Again, we work with unitless quantity, so we can make sense of having a perimeter equal to an area. That's just a normalization question. And here, so I put those holes around every one of those points, and I will send again epsilon to 0. Now, our result is that if omega epsilon is constructed as described just above, when I send epsilon goes to 0, the perimeter normalized Steklov eigenvalues converge to the area normalized Laplace eigenvalues of the problem in the original surface. And basically the method of proof here is to show, in fact, that in this specific situation, the classical methods of homogenization theory still go through, because I don't need every reference cell to be exactly the same. I can have auxiliary PDEs on all of those cells that will behave somewhat the same. I will not go into the details right now. Now, again, this means that large area normalized Laplace eigenvalues imply large perimeter normalized Steklov eigenvalues. And we've won. The first theorem I told you about today was Hersch's theorem. The largest Laplace eigenvalue on a sphere is 8 pi with the round metric. Well, so I can find a domain in S2 such that sigma 1 is arbitrarily close to 8 pi. There are minimal surfaces of genus 0 in the unit ball with perimeter as close to 8 pi as we want. And in fact, I can do that for surfaces of any genus. I can find a maximal Steklov eigenvalue as close as I want to a maximal Laplace eigenvalue on that specific surface. It's not only on spheres that I can do that. So we can even push this further in my work with, again, Alexandre and Misha Karpukin. We've proved that these supremums are in fact exactly the same. So not only an inequality of the Steklov being larger than the Laplace one, for every surface, every index k. And the proof here is based on an abstract definition of measure Laplacians and continuity results for eigenvalues of those Laplacians. So in fact, we have equalities here for a larger class of eigenvalue problems in general. Now, what have we done in the last 20 minutes? Well, we have solved the isoperimetric shape optimization problem for Steklov eigenvalues of surfaces without constraint on the number of boundary components. We have shown existence of some free boundary minimal surfaces with a larger perimeter than previously believed to be possible, and developed new homogenization methods intrinsically in a geometric context. Now, where does this go after that? Well, the homogenization business, it worked in every dimension. Actually, in the paper we wrote, we write about it in dimension D. The critical regime might change, but this works anyways. But the shape optimization bit used, just like in Hersch's theorem, the conformal invariance of the Dirichlet energy. And this is not true in higher dimension. And in order to use directly the homogenization theory, it will require to understand what happens when we have holes of size roughly proportional to the distance between them. Now, this has been done in the Euclidean setting, but at that scale, the geometry of the cells comes into play in a much stronger fashion. So here we need to find new techniques to take into account the fact that it's not every cell that looks exactly the same, but this is the challenge that we are looking into right now. And I think this is the right place to stop my presentation. Thank you for listening to me.